We will be discussing about Chemistry Paper 2 AS level structured question 2021 October-November, variant is 21 and the subject code is 9701. Carbon disulfide CS2 is a volatile liquid, that means it evaporates easily at room temperature and pressure. State the meaning of volatile. Volatile means it evaporates easily. Draw a dot and cross diagram of carbon disulfide. Carbon contains 4 outer electrons and sulfur contains 6 outer electrons. So they both forms covalent bonding and the bonding is shown. Suggest the bond angle of carbon disulfide. We can see that as there is no lone pair of electrons in carbon atom, thus they form a planar structure, so the bond angle would be 180 degree. Carbon disulfide is a liquid at room temperature while carbon dioxide is a gas. Explain what causes the difference in the physical properties of carbon disulfide and carbon dioxide. As we know that both are covalent compounds, but carbon disulfide contains more outer electrons or more electrons, so stronger induced dipole forces between its molecules. So, as carbon disulfide contains more electrons, thus more induced dipole or stronger induced dipole or stronger van der Waals forces of attraction between its molecules. Thus, it is liquid at room temperature. The enthalpy change of combustion of carbon disulfide is represented by the equation. Define enthalpy change of combustion. Enthalpy change of combustion is the energy change when 1 mole of a compound burns in excess oxygen. 1 mole of a compound burns in excess oxygen to form carbon dioxide and water. 1 mole of a compound burns in excess oxygen to form carbon dioxide and water. The table shows the enthalpy changes of formation. So enthalpy changes of formation, it shows the formation of carbon disulfide, carbon dioxide and sulfur dioxide. Use the data booklet, use the data that is given here to calculate the enthalpy change of combustion delta Hc of carbon disulfide. So for this equation that is given above, we have write this according to the order. Then we need to find this enthalpy change of combustion. So enthalpy change of combustion to find, first of all, as we have given the enthalpy change of formation, that means these compounds are formed. So the arrow would point towards this compound, carbon disulfide, carbon dioxide and sulfur dioxide. As we can see that as we have 2 sulfur dioxide, so its enthalpy is multiplied by 2. Then the arrows that are pointing in one direction is equal to the arrows that are pointing in other direction. We equate this to find the enthalpy change of combustion, that is negative 1077.7, that is approximately 1080. Negative 1080 is the enthalpy change of combustion of carbon disulfide. Hydrogen sulfide H2S is slightly soluble in water. It acts as a weak acid in aqueous solution. State what is meant by weak acid. So weak acid, that means it is partially ionized in aqueous solution. Give the formula of conjugate base of H2S. So the formula for conjugate base would be HS minus and the conjugate acid would be H plus. For example, here water reacts with HCl to form H3O positive and Cl negative. As we can see that here water acts as a conjugate acid because water acts as a conjugate base because it gains a hydrogen ion, while chloride acts as a conjugate acid as it gives the hydrogen ion. So acid is the proton donor, and if one proton is donated between the acid and the base, then the substance that gains the proton is the base, the substance that gives it would be acid. That means proton donor is an acid, and in this case chloride or HCl is a conjugate acid, while water is a conjugate base since it gains a proton or H plus ion. Similarly, here hydrogen ion is lost by this HS minus, so this is a conjugate base, while H plus ion is a conjugate acid. Also they are differ by a single charge. Then H2S reacts slowly with oxygen dissolved in water. The reaction is represented by the following equation: H2S plus oxygen water plus sulfur. Explain with reference to the oxidation numbers why the reaction is a redox reaction. So as we can see that sulfur has an oxidation state of -2 and is converted to 0. Therefore, sulfur is oxidized as its oxidation state increases from -2 to 0, while oxygen is reduced because its oxidation state decreases from 0 to -2. Its oxidation state decreases from 0 to -2 and therefore it is reduced, while sulfur in H2S is oxidized because its oxidation state increases from -2 to 0. The compound H2S3 is a common mineral. When H2S3 is heated in air, it forms a mixture of product as shown. A sample containing 0.198 gram of H2S3 is placed in 0.1 dm³ of pure oxygen and excess in the reaction chamber and is connected by a gas syringe at room temperature. So oxygen is in excess. The reactants are heated until no further changes are observed. The products are then allowed to cool to the room temperature. Calculate the volume in dm³ of the gas present at the end of this experiment. So we need to find the volume in dm³ of the gases that are present at the end of the experiment. We know that earlier, as oxygen is in excess, so it must be present at the end of the reaction since it is an excess. Also with oxygen, since sulfur dioxide is a gas and it is formed, so it is also present at the end of the reaction. So together with sulfur dioxide gas, some excess oxygen is left at the end of the reaction. The molar volume of gas is 24 dm³ per mole. Under these conditions, assume that the pressure is constant throughout the experiment. So you're working. So we need to calculate the total volume of gas at the end of this reaction. So to find the total volume of gas, as we know that oxygen is in excess, so first of all we need to find the volume of sulfur dioxide. So to calculate the volume of sulfur dioxide, we know that volume of a gas is equal to number of moles into molar gas volume, and we know the molar gas volume, that is 24 dm³. We just need to find the number of moles. To find the number of moles of sulfur dioxide, we first need to know the number of moles of H2S3. So number of moles of H2S3 would be its mass in grams divided by its mR, and the AR of AS is 74.9. After calculating, we get our answer as 8.045 into 10 to the power -4. Now for the number of moles of sulfur dioxide, as we can see that H2S3 is 2 moles while sulfur dioxide is 6 moles. So the mole ratio is 1:3. That means the mole that we have calculated, we divide it by 2 and multiply it by 6, or just multiply this by 3 since the mole ratio is 1:3. So the number of moles of sulfur dioxide would be number of moles of H2S3 into 3 because the mole ratio is 1:3. So we get the number of moles of sulfur dioxide. Now the volume of sulfur dioxide is equal to number of moles into molar gas volume. So the total volume of sulfur dioxide is given. Now we know that the volume of sulfur dioxide, and we also know that oxygen is in excess. That means it is also present at the end of the reaction. So we need to find the volume of oxygen that remains at the end of the reaction. So to find the volume of oxygen, we need to first find the number of moles of oxygen. We have given the volume of oxygen. So by using this, we calculate the number of moles of oxygen. Then we know the number of moles of oxygen. Now comparing with H2S3, that is the molar ratio of H2S3 and oxygen is 2:9. So by using this molar ratio, we know that 2 moles of H2S3 reacts with 9 moles of oxygen. That means the number of moles of oxygen that is reacting is its number of moles that we have calculated earlier into 2 into 9 by 2. So the number of moles of oxygen that is reacting would be, since we know that the total moles of oxygen, we know the total moles of oxygen is this, and the number of moles of oxygen that is reacting would be the number of moles of H2S3 into 9 by 2. We divide this mole by 2 to calculate the mole for 1 mole of oxygen, and for 9 mole of oxygen, since there is 9, we multiply this value by 9 to calculate the number of moles of oxygen that is reacting with H2S3 according to the balance equation. Since the molar ratio is 2:9, that is 2:9. So we know the number of moles of oxygen that is reacting, and we know the total moles of oxygen. So the number of moles of oxygen that remains would be total moles, that is this value, minus the moles that is reacting. After subtracting, we get the number of moles that remains at the end of the reaction. So this much mole, that is 5.4675 into 10^84 moles, remain at the end of the reaction. So this much mole remains at the end of the reaction. So the volume of oxygen that remains would be the number of moles into molar gas volume, that is 24. So we get the total volume of oxygen that remains at the end of the reaction. Now the total moles of gases that remains at the end of the reaction would be the volume of oxygen that remains plus the volume of sulfur dioxide that remains. So after adding, we get a total volume that is 0.071 dm cube as the total number of volumes of gases that remains at the end of the reaction. Again, in summary, first of all, as we have given the mass of H2S3 and the volume of oxygen, and we know that oxygen is in excess, we need to find the total volumes of gases at the end of the reaction. To find the total volume of gases, we know that sulfur dioxide is a gas, so we need to find its volume. Also, we know that oxygen is in excess, so we need to find the volume of oxygen that remains at the end of the reaction and add these two volumes. So first of all, to find the volume of sulfur dioxide, we need to find the number of moles of sulfur dioxide, and to find the number of moles of sulfur dioxide, we first find the number of moles of H2S3, then by comparing the molar ratio, we find the number of moles of sulfur dioxide, then volume of sulfur dioxide. Now we have to deal with oxygen. We first of all need to find the number of moles of oxygen that is given at the start of the reaction. Then by using the number of moles of H2S3, we need to find the number of moles of oxygen that is reacting by using the molar ratio. We know the number of moles of oxygen that is reacting and the total moles of oxygen. So we know that the oxygen is in excess, thus the oxygen that remains at the end of the reaction would be given. Then the volume of oxygen that remains at the end of the reaction is this much. Then we add the volume of sulfur dioxide with the volume of oxygen to find the total volume, that is 0.071 dm cube. This is a 4-mark question. Then state the environmental consequence of releasing sulfur dioxide into the atmosphere. Since sulfur dioxide is a greenhouse gas, and sulfur dioxide and nitrogen dioxide, they both causes acid rain. Sulfur dioxide can be removed from the air by reacting with sodium hydroxide. Consider the equation for sulfur dioxide and sodium hydroxide using the symbols. So sulfur dioxide is an acidic gas. It reacts with sodium hydroxide to form sulfur dioxide is an acidic gas. It reacts with sodium hydroxide base to form a salt and water, that is salt of sodium sulfite and water. Salt of sodium sulfite and water. Question number 2. The reaction scheme shows some reactions of calcium. Reaction 1 produces calcium nitrate and one other product. Identify the other product. So calcium reacts with nitric acid to form calcium nitrate and hydrogen. So one other product is hydrogen gas. Now construct the equation for the thermal decomposition of calcium nitrate. So calcium nitrate decomposes in a way that it forms calcium oxide, nitrogen dioxide and oxygen, and we need to balance it. We don't need to give a state symbol since it is 1-mark question. Then state the trend in the thermal stability of group 2 nitrates down the group. So the thermal stability for group 2 nitrates, sulfates and carbonates all increases down the group. That means thermal stability increases down the group. In reaction 3, carbon dioxide is bubbled through water containing calcium carbonate and a solution of calcium hydrogen carbonate forms. Construct the equation for this reaction. So for the reaction 3, calcium carbonate containing water is added to carbon dioxide and calcium hydrogen carbonate is formed. So calcium carbonate containing water, calcium carbonate is added and calcium hydrogen carbonate is formed. After balancing, we see that all are in 1:1 ratio. Describe how calcium hydroxide is used in agriculture. So calcium hydroxide is a base. It reacts with acidic soil to neutralize it. Calcium hydroxide is a base, so it reduces the acidity of the soil. In reaction 4, calcium carbide is found from calcium oxide. Calcium CaC2 contains C2 2- anion. Each carbon in C2 2- is sp hybridized. Describe how sp hybridized orbitals are formed. Since it is a 1-mark question, so we just need to define it. So by the combination of an s orbital with a p orbital forms sp hybridized orbitals. Now sketch a diagram to show how two sp hybridized orbitals form sigma bonds. We need to show how two sp hybridized orbitals form sigma bonds. So first of all, coming to this part, we need to know what is sp hybridized orbitals. So when an s orbital reacts with a p orbital, it forms sp hybridized orbitals as given by the explanation. So the sp hybridized orbitals would look something like p orbital, just is one side is elongated due to the presence of an s orbital. So this side is elongated due to the presence of an s orbital, and this is the nucleus of s and p orbital. Nucleus or the center of s and p orbital. This is the center of p orbital, and this is for the s orbital. So this is sp hybridized. Now, what is sigma bond? Sigma bonds are formed by head-on overlap of atomic orbitals, such as this is forming sigma bonds to s orbital, or this two p orbitals are forming sigma bonds. Now, we know that sigma bonds are formed by head-on overlap of atomic orbitals, such as this is an example, since it contains 1 electrons in this bond, or 1 bond length, or 1 bond hand. Since it contains 1 bond hand, so all the bonds forms as sigma bonds. But if it contains 2 or 3, then it would be 1 sigma bond and 2 pi bond. If it contains 5, then it will be 1 sigma bond and 4 pi bonds. That means the first bond is always the sigma bond, and the second bond or the third bond or the fifth bond is always pi bond. Except in the first bond, the rest of the bonds that would be formed between two atoms would be pi bond. Suppose these are all pi bonds that I am drawing, but the first bond is always a sigma bond, while the rest of the bond is a pi bond. And the sigma bonds are shown by this, that here carbon to carbon bond is as one bond hand is formed, so this is a sigma bond, and these are all sigma bonds, and this is represented by this diagram. Now for pi bonds are formed by sideways overlap of atomic orbitals. Sigma bonds are formed by head-on overlap, and pi bonds are formed by sideways overlap. Now for pi bond, we can see that these two p orbitals are overlapping sideways, not head-on. Head-on is represented by, suppose this is head-on forms sigma bonds, but by sideways overlap, that means this side and this side, they form pi bond. Also pi bond is represented by this diagram, that is two nucleus or two centers are shown by this, and the bond is represented by this. So you can represent pi bond either this or this. These two are the same. Pi bonds are formed by sideways overlap of atomic orbitals. For example, here we can see that the first bond is always a sigma bond, while the second bond, as we can see that a second bond is formed, there is pi bond. So pi bond is forming by sideways overlap, that is represented by this diagram. So these are sideways overlapping and forming pi bonds. So in summary, sigma bonds are formed by head-on overlap of atomic orbitals, while pi bonds are formed by sideways overlap of atomic orbitals. You can represent pi bond either in this way or this way, they both are the same, while sigma bonds are represented by this way. Now sketch a diagram to show how two sp orbitals or sp hybridized orbitals can form sigma bonds. So here we can see that this is the p orbital, it reacts with an s orbital, thus this side is become longer. So this is an sp hybridized orbital, and this is an sp hybridized orbital. They form sigma bonds by head-on overlap, so they head-on overlap and forming sigma bonds. Sigma bonds are formed by head-on overlap. Then in part D, the flowchart shows some reactions of calcium carbide. Reaction 5, can be used to prepare ammonia. So reaction 5 is used to prepare ammonia. It is also shown by here. Calculate the minimum mass in tons. We need to calculate the mass in tons of calcium cyanide that is required to produce 1.5 into 10 to the power 6 moles of ammonia. So we have given the mass of ammonia that we need to form from calcium cyanide. So first of all, we need to find the number of moles of ammonia that is formed. So mass in grams by AR or MR is the number of moles of ammonia, and since ammonia and calcium cyanide is 1:2 ratio, that means 2 moles of ammonia forms 1 mole of calcium cyanide. So 1 mole of ammonia would form 0.5 or 1/2 mole of calcium cyanide. So its number of moles of ammonia by 1/2 would give the number of moles of calcium cyanide. Then the mass of calcium cyanide would be its number of moles into AR or MR, which gives the mass of calcium cyanide in grams in tons. Since the mass of ammonia is also given in tons, so we have to calculate the mass of calcium cyanide in tons and give our answer in terms of tons. Then we need to draw the structure of the organic product formed from this reaction. So CH3CH2Br reacts with NaCN dissolved in ethanol. So it reacts with NaCN dissolved in ethanol to form CH3CH2CN. Here Br is replaced by Cn. Now this is an example of nucleophilic substitution reaction because NaCN is reacting with this Br and NaCN is dissolved in ethanol. But if suppose we have a double bond and here bond and HCN is reacting HCN, then it would be nucleophilic addition. That means the double bond brings a hydrogen would attach to one carbon and CN is attached to the second carbon. But for now, nucleophilic substitution occurs since the nucleophile Br is replaced by the nucleophile Cn in presence of NaCN in ethanol. So NaCN in ethanol reacts with Br to form Cn, and this Cn goes acidic hydrolysis, that is H2SO4, and is aqueous. So acidic hydrolysis, that means here we can say that H2SO4 and water is present. Since it is aqueous, so water is present and heat under reflux to form COOH, that is Cn is converted to COOH, and here acidic hydrolysis occurs of Cn. Now the next part, NaCN in HCN catalyst. So HCN is reacting in presence of NaCN catalyst. So as HCN is reacting, thus I have said that here nucleophilic addition occurs and HCN is present, so H goes to this oxygen and Cn is going at this bond. So it forms CH3COH Cn CH3. So here we can see that nucleophilic addition reaction occurs since HCN is present and HCN is reacting in presence of NaCN catalyst. Here NaCN is acting as a catalyst, while here NaCN is reacting because there is no HCN present and NaCN is dissolved in ethanol. Thus nucleophilic substitution reaction occurs, while as HCN is reacting and double bond is only broken, thus there is no substitution occurs and nucleophilic addition reaction occurs. So the structure is also represented by here OH and Cn, that is OH and Cn. This is a reactive period 3 element. Phosphorus has several allotropes. Details of the two allotropes are given. So allotropes are different forms of phosphorus. Allotropes of phosphorus P4 and P, that is white phosphorus and red phosphorus. White phosphorus has a melting point of 41, that is low melting point, while red phosphorus has a higher melting point. White phosphorus and red phosphorus are both have covalent bonding. Suggest the type of structure shown by white phosphorus and red phosphorus. So white phosphorus, that means P4, has lower melting point, thus it has simple molecular structure, while red phosphorus has a higher melting point, so it has giant molecular structure. So as it has simple molecular structure, that means it has weak intermolecular forces of attraction, while P has strong covalent bonds, because it has giant molecular structure, so it has strong covalent bonds. So more energy is required to break the covalent bond than to break the intermolecular forces of attraction. More energy is required to break the covalent bond than to break the strong forces of attraction. Red phosphorus P and white phosphorus P4 are exposed to sunlight. Use this information to draw a reaction pathway diagram to show the formation of red phosphorus from white phosphorus. So red phosphorus is formed from white phosphorus, and as the enthalpy change is negative, thus the red phosphorus would be below and P4 would be above. And here we can see that 1 by 4 P4 forms P, and 1 P4 thus form 1 P4 would form 4P. So there is 4P, and it is a 1 mark question. Then the second part, sum of the reactions of P4 is shown by the reaction scheme. State the oxidation number of phosphorus in P4O10. So for P4O10, we can see that oxygen has an oxidation of -2 and 10 oxygen, so it has a total of -20. To balance this -20, we have 4 phosphorus, so 4x. So 4x is equal to 20, that is x is equal to 5. So the value of x is plus 5, and to balance this plus 5, that means plus 5 into 4, that is plus 20, is equal to minus 20, that is the overall becomes 0. So this will be plus 5. Reduce the identity of Q and hence consider the equation for reaction 1 and 2. So for Q, we can say that PCl5 reacts with water, it forms POCl3 and HCl. But since PCl5 reacts with water to form a product that is same as P4O10 reacts with water, so as they are forming the same product, so this would not be the answer, and the answer would be H3PO4 and HCl. When PCl5 reacts with water, it forms H3PO4 and HCl, and P4O10 reacts with water to form H3PO4, and the common product is H3PO4, that is formed by these two reactions. Then triphosphine is used in a type of reaction shown by weighting reaction. Give the empirical formula of triphenylphosphine. So there is one phosphorus, and this one group is represented by C6H5. That means this is C6H5, this is C6H5, and this is also C6H5. That means one phosphorus and 3 C6H5. That means in total we have 18 carbon, 15 hydrogen, and 1 phosphorus. In a weighting reaction, an aldehyde, that is this aldehyde, CO group, reacts with a halogenoalkane, that is this halogenoalkane, to form an alkene, that is this double bond compound. The conversion is shown by the unbalanced equation. Compound H can be made from propanol. So compound H can be made from propanol. Stage 3 of this reaction scheme is shown by weighting reaction. So the stage 3 is the weighting reaction, and initial reactions are at the start of these reactions. H can be made from propanol. Okay, so for the first stage, so first of all read the question. State the type of reaction that occurs in the first and the second stage. So for the first stage, we can say that your aldehyde, that is COH group, reacts with NaBH4. As it reacts with NaBH4, thus NaBH4 is a reducing agent, thus reduction occurs, and your OH and H is formed by breaking of double bond. So OH and H is formed by the breaking of double bond, that is represented by G. So as the double bond breaks and a hydrogen is attached, and so reduction occurs. Since hydrogen is attached, so reduction occurs. So this is the reduction, and the reducing agent is NaBH4. It can either be NaBH4, LiLH4 in dry ether, or hydrogen in presence of nickel catalyst. Then for the second stage, we can see that G, that means this substance, is converted to reacted with iodine. So this substance reacts with iodine, and nucleophilic substitution reaction occurs, since the nucleophile OH is replaced by iodine, and it will form C2H5, Ci and HH. So here basically OH is replaced by iodine. So this is the example of nucleophilic substitution reaction. So the structure of G is shown and the structure is of H, and the structure that is found from G is this, and this substance that is C2H5 Ci, then it reacts with an aldehyde to form, as we know that initially aldehyde reacts with halogen aldehyde reacts with halogen to form an alkene. Thus this aldehyde reacts with this halogen to form an alkene, and here basically from aldehyde CO is removed, and from halogen alkyl I and H is removed, and here double bond is formed, that is C2H5CH, C2H5CH, that is this substance, and from aldehyde C2H5H, that is this C2H5H, and after removing this oxygen and HI, here double bond is found. That is initially this is given that aldehyde reacts with halogen alkane to form alkene. Then in the next part, identify the organic product formed. The organic products that are formed when compound J, shown below, is heated with hot concentrated acidified KMnO4. So when J reacts with hot concentrated KMnO4, as it reacts with KMnO4 and it is hot concentrated, so the double bond will break, and as it contains one alkyl group and one hydrogen, so it would be converted to carboxylic acid, that is represented by this structure, and this side, as it contains two alkyl groups, so this would form a ketone, that is CO group is attached after breaking the double bond. So then in the next part, in question number 4, compound B is a liquid with a fruity smell. That means compound B is a ester. Reaction 1 is an oxidation reaction. Give the reagent and the condition for reaction 1. So for the reaction 1, we can see that alcohol is converted to carboxylic acid. That means this is an reaction with acidified K2Cr2O7 and heat under distillation. So instead of distillation, it would be heat under reflux, since it forms carboxylic acid instead of ketone, instead of aldehyde. So as carboxylic acid is formed instead of aldehyde, so it would be heat under reflux and K2Cr2O7 is acidified. Then consider the equation for reaction 1. So for reaction 1, we can see that alcohol reacts with oxygen to form carboxylic acid and water. Alcohol reacts with oxygen to form carboxylic acid and water, or oxygen from oxidizing agent. Then suggest the type of reaction that occurs in reaction 2. For reaction 2, we can see that carboxylic acid is converted to, here carboxylic acid parts remains the same, just H is converted to H in CH3, that is this H, that is CH3's H is converted to Br. So H is replaced by Br, that means this is a nucleophilic substitution reaction. Then H2SO4 acts as a homogeneous catalyst. As it is an homogeneous catalyst, that means it has the same phase or same state as the reactants. Same state as the reactants. That means if the reactants is a gas, then catalyst would be a gas. If the reactant is solid, then the catalyst is also a solid. Then the next part, reaction 2 needs to take place in the absence of water. In the absence of water to prevent the formation of compound C. If C is present in the reaction mixture of the reaction 3, a defined compound D will also form. Compound D has two identical functional groups. The infrared spectrum of D shows a strong absorption at 1100 to 1700 centimeter per centimeter, but no absorption due to OH group. Use a data booklet to identify the functional group of D. Compound D shows a strong absorption at 1100 and 1700 per cm. That means it can either be CO, C double bond, or C double bond O. But it can be C double bond because it shows a strong absorption. But as we can see that here in C double bond, it shows a weak absorption. So this can be the answer. So this could be either CO or C double bond O. That means it must be an ester, that is CO, C double. For example, that is it will be an ester because it can be a carboxylic acid or an alcohol, because if D would be a carboxylic acid or an alcohol, then it would be same structure as C. Thus, it must be an ester. So D is an ester, as at 11,000 per cm, 1100 per cm is linked to CO, and 1720 per cm is linked to C double bond O. But it can be COH, that means carboxylic acid or alcohol, because otherwise we cannot differentiate between C and D, because both C and D would be the same, because if D contains carboxylic acid and alcohol, then C and D would be the same. That means D must be an ester. Part C. Some other reactions of C are shown. Draw the structure of E. So for the structure of E, we know that carboxylic acid and alcohol is converted to E, and as sodium carbonate is reacted, so sodium carbonate or sodium hydroxide is only reacted with carboxylic acid, and it does not react with alcohol. So it does not react with alcohol, so it reacts with carboxylic acid, and OH is replaced by Na. OH, not OH, that is from OH, H is replaced by Na, and it will be ONA, that is ONA structure, and the rest remains the same, since Na2CO3 and NaOH has no effect on alcohol. Suggest why NaBH4 is not a suitable reducing agent for F to make F this structure from C. We know that NaBH4 is used to reduce any substance, but it can be an carboxylic acid, and as we know that the structure of C, from the structure of C we can see that here carboxylic acid is present, and carboxylic acid cannot be reduced by NaBH4 or hydrogen in presence of nickel catalyst. Carboxylic acid is only reduced by LiAlH4 in dry ether, so NaBH4 is not a strong reducing agent. And here we can see that NaBH4 can reduce OH group, but as we can see that OH remains the same, so it has no effect of NaBH4, and OH is not further reduced. Consider the equation for the reaction of CH2OH2 with SOCl2. So CH2OH2 reacts with SOCl2 to form CH2Cl, SO2 and H2O. That means here just the reaction occurs with CH2OH reacts with SOCl2 to form, here OH is replaced by Cl, so H is replaced by Cl, and sulfur dioxide and water is formed as our byproduct. Explain why C is very soluble in water. So for the structure of C, we can see that here OH group is present, so it forms hydrogen bonding with water, that is this hydrogen bond by the hydrogen of one water molecule to the oxygen of another water molecule. Thus C would form hydrogen bonds with water, thus it is soluble in water.